Recording in progress.
Okay. All right. Welcome everybody to the Lab 1 help session. So what we are going to do today is we are going to go through solving an equation using or designing a circuit from an equation, building that in Quartus, building the truth table, voltage table, and simulating that circuit in Quartus. And if there's anything else that you want added to the review as we go along, anything you don't understand, please just let me know. I just did what should be like the basic building blocks that you repeat, I think like 5 times. Okay. Yep. All right. Okay, so the first thing we're going to do is just draw an equation or a circuit from this equation. And this equation specifically, I made so that we could just use two NOR gates. So you're welcome to follow along drawing the circuit yourself and then also drawing it in Quartus. Okay. So the first thing I'm going to do is draw all of the inputs as just their letters and then leave these open. Okay. All right. So we need sorry. Okay, so we need two NOR gates. So the first one is going to be B and C. Or sorry, we need two OR gates, but I'm just going to tell you that they're NOR because that's how I cooked it up. So for B, I'm just going to do active low because that makes this B naught as it shows here. And then for C, I'm going to make it active high as it shows here. And then we know that this output, B naught or C, is going to be knotted. So I know that the next gate I'm going to draw with positive logic for the beginning so that it gets knotted. All right, and then A here, it is not knotted or there's no negation. That's a little confusing. So I'm just going to make this high and bring that into there. And then this is going to be A or not B or C, knotted. And now I wanted to use two NOR gates because remember in your labs, for lab 1 at least, you're restricted to using two NORs and two NANDs. So I could put an OR here. However, since you're building this physically, I wanted to show you when you're constricted, what else you can do. So I'm just going to make this output active low. Okay, so that way it's not negated, and that way this matches this. Okay, that was more of a mixed logic review. Does all of that make sense? Okay, so I'm just going to jump into Quartus now. Yeah, we'll go ahead and share. Right, so the first thing I'm going to do is talk a little bit about the file situation. So I would recommend everyone uses their on-device storage for the files because OneDrive can be a little messy. I know it works a lot of the time, but I think the problems come in when stuff gets stored in the cloud and then deleted from your device, and then Quartus doesn't know where it went. So what I did to get this file in the right place was I went to my, let's see, PC and then OS. And then under users, you should have your name and some sort of documents file. It usually should just be documents. Yeah. So on this local file or this local folder, then I'm going to make another folder. So I would suggest that you have a folder for each of your labs because you're going to have multiple project directories for each lab. So I think you already have lab 1A through 1D. So it's 4 different projects. So it's really helpful to keep everything organized. So that way you know where stuff is. And then in lab 3, you're going to use a design from lab 2. So you want to know where exactly it is. Okay, and it's also helpful for your lab quizzes because you're going to be short on time. So knowing exactly where it is very helpful. Okay, So this was the folder I made earlier, but I'm just going to make a new folder, and this is going to be for my project because every project needs its own folder that Quartus can put all of its files into. Okay, so I'm just going to make it lab one and then HS for help session. All right, and then in Quartus, I'm going to try to go through these steps pretty slowly. I've had a lot of people with issues later down the line because these steps weren't followed properly. You can always pull up the Quartus tutorial to see exactly what steps you need to take. So if I pressed new project wizard, let's get rid of that. All right, so next, and I'm going to navigate to exactly where I had my file. So, and you can also pin it somewhere up here. I think I meant to and then forgot. But let's see, go back to users. All right, so I'm going to select the folder I made. This is for the project. And I'm going to name the project exactly what the folder's name is. So lab1 HS. All right, and then we're gonna make an empty project. In this course, we never actually use project templates, so just leave this as it is. All right, and then I'm not adding any files. In the future, you might want to, or if maybe you have to make a new Quartus project for something that went wrong, but generally you don't add any files. All right, and then for now, I'm going to do the max 10 because that is what we're going to be using for every single lab afterward. And the reason why we click board, max 10, and then D10 light, so this one, and then also deselect, create top level design file. If you forget to do that, you can always choose files and click it afterward, make it the top level design entity. But the reason we choose the DE10 Lite is because the DE10 Lite that you got in your lab 0 can be programmed with logic gates because it has a built-in FPGA. So we use this so that when it compiles, it knows what device it's going to. Because we can't, for example, if we use like a Cyclone 5 device, but then we plugged in a Max 10 to program it, it would have no idea what it is. So that's why we do Max 10, DE10 Lite. And then we always do Model Sim VHDL. Model Sim is just the better simulator, the one that you all installed that did not require a license. And VHDL is just what we always use. We're also starting in lab, I think 4 or 5. You're going to be typing a little bit of VHDL. So we always just want to use VHDL from the beginning. Right, and I think that's it. Right. Maybe I'm going to grab your. Let's do that. Okay.
Do you need nuts?
No, I'll grab my own computer so I can show you stuff. Okay. This. Okay.
Who needs a screenshot? Oh, okay. No, no.
Yeah. Okay. Well, I'm just pulling up the circuit I made already. So if you have it, that's great. If not, don't worry about it because I'm just gonna rebuild the same thing. But it's helpful to draw it out because that way, super simple to rebuild it. Okay, so I'm gonna make a new BDF. I have this option here. I don't know what to do with this. I have this option here for making a new BDF. But if you don't, you can just select File, New Block Diagram. And I believe you can get that from one of the view options, but we can go over that later if you want that. Okay, so then if you double click just in here, you'll get this box to put in wherever you want. So the first thing I'm going to do is label my inputs. Okay, so I'm going to press repeat insert mode and place these here. So I have 3, and they don't have to be like, well, you can organize them, but not when you first place them. All right, and then 1 output. All right, and then actually what I should have done first, but as long as you have it, you want to make sure you put your name. And then your lab. So you would have like lab 1, part X. So it's broken up into five different parts. So you would put part 1 through 5, depending on what you're working on, so that your Pi knows. And then you have your Pi name. So the first and last name of your Pi, again, so that they know it's yours. Right. And then a description. I think I'm missing something else. Class number. Okay, yeah. So your class number. So this is your 5-digit class number that you can find on 1UF or probably any of the lab quizzes. There's probably plenty of places to find it, but you can just go to 1UF and see what you're registered for. So that's 5 digits. And then description, which is kind of misleading because it's not really a physical description, it's just the equation that you're using. Um, and then maybe later down the line you can write, this is a BDF for a counter or whatever you're designing. So I'm just going to write the equation that I had earlier. All right, so A for, okay. All right, so that's important to have in all of your BDFs. Right? And then I'm going to draw or get the first NOR gate and then get another one. Right? And then, so the input to the first one, it was B active low. So we denote the active low signals with an underscore and an L. You don't have to denote the high signals with anything, the active high signals. You can put an H if you like, but to make it less cluttered, just don't put anything and then only denote the low ones. All right. And then another thing is make sure your wires are connected. I've seen a lot of BDFs where the wires are not connected pretty much at all. So if there's like a big bubble here, or if there's an X, so you see this X right here. So that means it's not connected to anything. So if there's an X, like right at the input of your NOR gate, it's probably not connected to anything. And it will not let you simulate or probably compile anything because it'll throw you an error. All right. And then this output is going to go to this input. See, okay, so this is exactly what I was talking about. There's that big bubble, which is like it doesn't know what to do with, and then this X right here. So to fix it, you can just click on the X, move it over there, and it fixes it to a straight line. Okay. That has been throwing a lot of people errors. Okay, so I'm just going to write here what the intermediate equation is. This is not something you have to do for all of your BDFs, but it's pretty helpful, especially if you have a simpler one and you just want to keep track of everything. Right. And then this I'm just going to bring out, and this was an active high. Okay. And then we had our active low signal, which was F low. And I'm going to name these A, B, L, C, and then F low. And when you put them all together, you can pretty quickly name things just by like pressing enter. Okay. And then if I compile it, it should work. You always just leave the name whatever it is. The default name will just be whatever you made your project, which is really very helpful because when you go to look for it and you have a BDF named exactly what you need it to be, then you'll know what you're looking for. Okay, does anyone have any questions going from equation to mixed logic circuit to Quartus design? Okay, all right. And then the other thing that you can either do on paper or in Quartus or both is if you go to the website and then software docs, you can choose any of these. I like the Pinouts of Common Parts website because it loads really fast and it shows you the gate. So these are O2s that we're working with. So I can go ahead and do this. So this is helpful for when you're actually building your circuits so that you know exactly what pin your inputs are going to. So I'm going to make this the first 7402. And if you had more than 4 gates of the same kind, you would put 7402A, 7402B. So and so on. Okay, that was just in the, okay. All right, so you can label that there, and then you can put, so looking here, the first inputs are 2 and 3. So you put that here, put this here, and then the output is 1. I think you do this in homework 3, if I'm not mistaken, but it's something you should do for the lab, and any circuit you're building in the class. All right, then moving on to the second one. This is also 7402. And then we have 5, 6, and then 4. And as you can kind of notice, 4 is the output, and it's not really in accounting order like it is for this one, which is why it's important to pull this up so that you don't mess it up. Because if you put an input into pin 1 for a NOR gate, it won't work. It might blow the pin because it's getting a voltage into an output. But yeah, it should be fine as long as you follow the pin diagram. Okay. All right, now moving on to the truth table. This is probably the part that most people have had confusion with. So because there are 3 inputs, I know that there's going to be 8 rows because it's 2 to the power of 3. That's just a good way of knowing it. So I'm going to do 9, can't. Okay, so I'm going to add like 3 more. Okay. Okay. So these can be bolded because they're the titles. So a good way to do it is just say 0, 1, 0, 1, 0, 1. So every other one you skip for the first one, and then for the second one, every 2 you skip. So 0, 0, 1, 1, like that. And then for the third one, it's every 4 you skip. So it's going up by a power of, it's 2 to the power of, yeah. So you're doubling how many you skip every time you move left 1. Go higher in the bit priority. Significance. Higher bit significance, you double. So yeah. So this will be 4. And then if you had a 4th input, which I believe you do for lab 1, you would do all 8 of these zeros, and then the second half of the rows would be another 8 ones. Does that make sense? Okay. It's a lot faster than counting out 0, 1, 2, and figuring out what that is in binary, which is what I did at the very beginning of when I did lab 1. It was very confusing. Okay. So then for the truth table, we're going to label our intermediate steps. So we have, I'll show you here. We have B naught, which is right here, and then not B or C. And then we finally have F. So right here, we're going to do not B. And then that's pretty easy. You can just look at the B's and change them. So where there's a 0, there's going to be a 1, and so on. Okay. And then now we have not B or C. Okay. So now, because I have the not B column, I don't have to worry about this and inverting it and doing all that in my head. I can just look at not B or C. So since it's an or, I like it much better than having to do the and ones, because wherever there's a 1, I can just say it's going to be true. So it's going to be false here. Okay. And then, all right, so now we have not B, and C. Like I said, it's really easy to do this when you label every single intermediate expression, which is why I know it looks a little tedious, but it makes it much easier and you make less mistakes this way. Okay, so I'm just going to reverse all of these. Okay. And then the final expression, which I can denote just as F because it's equal to F equals A and not B and C. Or sorry, A or not B or C. Okay. So I'm just going to look at this equation or this column and this column. So I know these are all ones. So I'm just going to stick them here. And then there's one here. I'm just going to make these 0. Okay, so that is a complete truth table. Does every step of that make sense? Okay, and you saw there's a couple shortcuts. Don't be counting out binary and doing it that way.
Enable the figure.
Label the figure, yes. Yeah, so have, I think I trapped myself into just the table. Okay, yeah, so have like, I always wrote figures in table differently. So I would have table 1, truth table, or obsession equation, because I'm too lazy to write the actual equation. And then down here, you can have table 2, voltage table. Okay. So now when I do my voltage tables, I just copy and paste the truth table. Okay. And then delete all the intermediate steps because the truth or the voltage table helps you to just look at the inputs and the outputs. Because when you build it on your board, you're going to have switches, which are your inputs, and all you're going to see is the output. So that's all you really care about. Like I said, this helps you do the truth table without any mistakes or without many mistakes, but this helps you test your design, the voltage table. So they're both very, very important, right? And I'm going to go ahead and add my activation level. So A was high, B was low, C was high, and then F was low. Okay. So then to change all of these, definitely don't do it manually. We're going to start with these ones. I like to just highlight them and then go to the setting, which I have no idea where it is, but I always type in replace and it comes up.
You can also do Control-A.
Control H. I'll be doing that now. Okay. So if it's active high and I have 0, what am I going to replace it with? L or H? Perfect. Okay, so I'm gonna press replace all, but then it's gonna ask me if I want to search the rest of the document, and I'm gonna say no because I don't want it to mess up all the other columns. Okay. And then I'm gonna press Control H. All right, and then we know that the reverse is just gonna be this. Cool. All right. Now for active low, if I have 0, do I put L or H? Yes, put H. Because if it's false, it'll be low. No, if it's false, it'll be high, as if I didn't just ask that. Sorry. And then again, opposite here, right? And then when I have a bunch of columns and they're not necessarily all next to each other, like highs next to each other, lows next to each other, I like to just go to whichever setting I did last. So I just did low, so I can go here. I know this is correct, whatever this setting is, replace it. See what else I have to do. I have to do zeros. This is active low, so zeros are going to be replaced with H's. Replace those, right? And then these are active high, so it's the same situation as A, where 0 is going to be low. And then 1 is going to be H. Right? And so now they're all converted, but the thing is, Quartus does not understand mixed logic. Quartus only understands ones and zeros to represent low and high voltages. So you have to reorder your truth table or your voltage table to match the counting order if you want to use a counting order simulation. Does that make sense? So if I just ran the simulation and compared it to this, it would be like all messed up. I could look for maybe one row at a time, but your Pi is not going to do that. So we're going to reorder it. Landon actually has a better way. What I always did was I would take like low, 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 take this row. So highlight the whole row, just drag, just drag it to the top because I know that's 0. Because low, low, low would be 0, 0, 0 in Quartus. So that's starting at 0. But Landon has a better way if you want to. Do you want to show? Okay. Be 0.
Okay. Yeah. So it's not like necessarily a better way, but depending on how big your table is, it could be more efficient. So we just use this temporary right column to do our order. So the next one in counting order is low, 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 high. So we'll look and we see, oh, low, low, high. Oh yeah, I'm sorry, this is F. Yeah, yeah. So low, low, high is this one. So this will be like our 1. And then we just continue looking for them and labeling. So then this would be 3, 4, 5. And then, yeah, we'll just keep brute forcing this thing. What is it? 6, 7. So now we have all these columns 0 through 7. Um, so this one was like moved originally, but normally after you do this, you can do it faster because there's a pattern. This one was originally right here, so it'd be like 2, 3, 0, 1, 6, 7, 4, 5. So like, okay, yeah. So then you highlight this column, and then you can go sort. I think it's this button right here, and we're gonna sort by number in ascending order. Uh, I haven't done this in a minute. The entry is not that. Oh, word. Yeah, let's see.
On the graph to the left, let me sort by.
Oh, yeah. True. Okay, column 5. Good find, good find. All right. So we sort this, and now this is 0 through 7. And then, yeah, so low, low, low to high, high, high. So yeah, that was kind of a long-winded explanation, and then you can delete this. Wait, let me delete this top one. Yeah, but might get a little faster when you have bigger ones. But
Yeah. Okay, so that's a little bit easier than just dragging it. I know I was sitting with Jasleen and we were dragging it. Does everybody understand how we got the numbers though? Okay, so we just don't really care about what activation level it is for the sorting sake and for Quartus's sake, a low is a 0 and a 1 is a high. And that way we can get numbers from that. And then Quartus will do a counting order simulation, which I believe is the next item on our agenda, right? So I've done my compilation. I think it took a bit because my computer was not on battery, so I let it run, and now we can open up a new university program VWF, which is a waveform. And then I like to, well, I'll pull in my inputs first. So you can just double click here, press node finder, list, move them all over, okay? Right, and then because we have a bunch of inputs, we don't want to manually drag and decide what our 1s and 0s are going to be. So you can press shift click to highlight all of them. So if you had more inputs, it would be more useful. And then right click, group them together. I like to just label them inputs. And maybe in another lab, you would have outputs as well because they'll get more complicated. And then if you press this C right here, I believe in one of the lab documents, he has the clock highlighted, or like one of them's wrong. And I should probably bring that up. But the C is for counting. The clock symbol, you can barely tell it's a clock, but this is a clock, and it's for when we use a clock input starting in lab 3. So if we click the count value, then I like to make all of my periods or my grids 25 nanoseconds. So I'm going to have it count every 25 nanoseconds, right? And then I'm going to change my grid size again to that 25 nanoseconds. I believe it's recommended in the Quartus tutorial or something like that. I just always use 25. And then you want your Pi to be able to see what you're simulating. So since there's 8 different combinations of outputs, again, or different 8 different combinations of inputs. Again, those 8 rows in the truth and voltage tables. I'm just going to multiply 8 by 25 to get the 200 seconds that I need. So I'm going to change the end time to 200 nanoseconds. And that way I can see exactly what I need just on here, and you can see it stops at the 111, which is the limit of what our combinations can be. All right, so I can go ahead and functionally simulate. And then don't change the name of the waveform. It just makes it easier, or sometimes you can mess up the functionality if you do, and just save it exactly where it tells you to. Because if you did the setup right, it will have all of these folders and you just press save. You don't touch anything, you don't adjust anything, it just does it. Right. Okay, so now, since these are in counting order along with our voltage table, we can take this and compare them equally. Okay, so for 0, 0, 0, or low, 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 it's expecting low, which is right here. And then you can see this pattern of we're expecting 3 highs, 1, 2, 3, and then 4 lows, 1, 2, 3, 4. So that is pretty much what you will do like 5 times in lab 1. And I believe that covers pretty much everything. I do want to show you the timing simulation. So I believe this is the only lab where you'll actually have to use the timing simulation. But what you can do is if you follow the same steps I did, you can press assignments. You can change your device by clicking device and then changing the family to max 5. And then somewhere it's noted, but you're supposed to use the very first one and you press OK. And then instead of redoing the entire simulation waveform, I'm just going to press open. And sometimes you may not see it right away, but if you click down here to file types and just press all files, you can get your waveform back. So that's something I figured out like halfway through the course, and I was like, oh, I don't have to redo all of these waveforms before I get to run them again. Okay, so again, all the same settings that we had before. Now, if I change the simulation settings to VHDL, this should let me do a timing simulation. I did not. Okay. And apparently you press restore defaults. Do we do VHDL? Okay. So it's the restore defaults button that you have to press.
Yeah, you can compile.
Very, very true. That's exactly what I did not do. Okay, so if you change your device, you have to recompile. I did that earlier and it worked. Completely forgot to do it now. Yeah, like I said earlier, it's compiling it, and right now it's fitting it to the board that we specified. So you can actually see the different things. So analysis and synthesis is the light version one, where it's just for the simulator and just for like you to see that it works. The fitter right here is what actually allows it to map to the physical FPGA. And then assembler, I guess, does programming stuff. I don't really know. Timing analysis is what we're looking for when we're doing this. EDA netlist writer, I think it just has to do with the netlist of calculating what the output should be. Okay. Now if I open the waveform, it should work. Okay, so this is the propagation delay that Schwartz was talking about, I'm sure, with the physical chips that lets you emulate. So you can see this is the same pattern as before, but it's shifted over a little bit because there's that delay getting out of the chip. And this is also on the nanosecond scale. So it seems very, like it really is delayed a lot, but in reality, not really. And then also what you can do is I was unable to switch back to max 10 as he was also in the Quartus tutorial. But since we're not mapping this to the FPGA, you do not need to switch back to max 10. What you can do is just click simulation and run a functional simulation. And I don't remember if you need this for lab 1 or not, but if you do, again, this is the only lab you have to do the timing simulations. Everything else will be max 10, and then you map it to your D10. You can do this as well. So this helps you just look at the simulation and match it to your voltage table easier versus this one. So yeah, you can look at them at the same time. So you have the regular functional, which you'll be working with for the rest of the class, and then the timing, which is just to emphasize physical chips being delayed. So I believe that's everything I wanted to cover.
Now we're gonna do the physical.
So now we're going to do the physical
Got
implementation.
waveforms.
We do have waveforms on this bad boy.
D10 something power and ground.
Okay.
Put it here. All right.
So it's like an older classroom, so we don't have the top-down camera I was counting on. You have a USB-C. Yeah. So what we're gonna do is I'm gonna join on my iPad and then film it, or yeah, and then screen share it up there. And we'll see how that goes. Okay. All right, so for most of you, this should be pretty much a review because this is essentially what we did in the Lab 0 demo, just with more chips.
Okay.
Okay, so first, okay. All right, so since I don't have my D10 light, I'm getting power and ground from the DAD. So I'm gonna open up waveforms and then supplies. This is how I'll supply it, and I just need 5 volts. Oh yeah, I'm sorry. This class we use 3.3. Sorry. And then we'll start it. So a good rule of thumb is when you're physically working with hardware is don't touch the breadboard when power's on. So when we work with 3.3 volts, I mean, you're not gonna die or actually probably really feel anything, but it's a good habit to get into because all you EEs and CPEs might actually work with something. If you go into the power industry, you're gonna want to turn that off. So, okay,
In the design labs. Because
design labs.
Yeah, because our power supplies could do what, 30 amps?
30 amps,
I
which is a
think, which is
lot.
bad if you get
Ish.
that to your skin.
But that's out of the scope of this class.
Yeah, that's
But
chaos.
yeah. Okay, so we're gonna look at this breadboard real quick. So I already, before, I breadboarded the circuit that Joseph did on Quartus. So this should all look familiar. Here's our switch dip package, our SIP resistor, which is single inline package. This is the 7402 chip right here. So you might be able to read that O2. Oh, that's actually, that's pretty good. And then this is what the dip resistor I have. For all of you guys, it'll be this green PCB, and you'll see the traces. And then this is our LED package.
Which will also be white on the top. The old ones just had a red film over them.
Yes. So let's go ahead and do this because let's see. Yeah, we'll do the we'll split screen with the voltage table. Would that be?
Yeah.
Oh, okay, this is good. Oh yeah, okay, we're cooking now. Okay. So the reason we make this voltage table is to make this hardware kind of design and verification process super smooth. So if all of your switches are flipped upwards, so I intuitively have this first one as A, B, and C. When they're flipped upward, corresponds to a low on your voltage table. So it might not make sense because, if it's flip up, it's high. And then we can kind of like go through like why this works with the switch and LED circuit, but that's kind of a separate issue. So currently, when it's up or low, which is the voltage it'll be supplying. So now you can see that the LED is on. And a lot of students are like, that doesn't make a lot of sense because you can see that the output is low. So wouldn't you expect a high voltage to turn on the LED? but this is exactly why we learn how to wire our output or our LED the way we do. So right now it's wired as an active low LED. So if you can see, this brown wire is going to be our output signal. So in this case, it's a low, and it's going in to this end of the LED circuit, which is our cathode. And you know this because there's no writing on the dip package. And then on this other side, we do have writing. That's our anode, and it's wired into VCC or 3.3 volts. So I assume most of you haven't taken circuits, but all an LED is a diode, or light emitting diode is what LED stands for. And it basically turns on when there's some sort of potential difference across the two nodes. So in this case, our output signal is a low, and we have this high being supplied to our anode, which is why the light is on. So we'll go ahead and step through this table, and hopefully the LED will match with our output. So the next part of the table is low, low, high. So we're just going to take this third switch and we're going to flip it down for high. And you can see the light turns off. This is because currently on this brown wire, there's a high voltage, and there's also a high voltage on the anode side. So if you have 3.3 minus 3.3, that's 0 volts and the light won't turn on, right?
Yes.
The blue wires on the switches, are those like what makes it low? The inputs?
No. Okay. So I'm actually a good question, because this is kind of a common misconception. So I said on the LED, you have to flip the package depending on the activation level. For the switches, the activation level completely is, for the purpose of this breadboard, it's kind of mitigated when we create our voltage table. So remember when we create our voltage table and it becomes out of order, we switch it so that we can intuitively look at it on a breadboard. So on a breadboard, all active high and active low switches are wired the same. What determines the activation level is whether or not it's in the true position when it's open or whether it's closed. So there's a video on YouTube that explains this very well. So if you haven't seen that, I would highly recommend watching it. So does that kind of answer your question? Yeah, regardless, the setup for like this left side of the circuit, you'll always wire it the same. We have our voltage going into this dot on the SIP resistor. It crosses our switch package, and then on this side, it's all grounded. Same thing, active high, active low. All right, so now we're at low, low, high, and we're getting a high voltage, and we're expecting the next two input combinations to also have a high. So this is low, high, low, and then low, high, high. So now, as we go to high, low, low, we should expect to return back to this low value and the light will turn on. So let's try that. So I'll flip this first one. Now we have high, low, low, and the light is on. And then I'll go ahead and go through the other combinations just to prove that it works. But the light should stay on since we continuously have low signals. So this is high, low, high, low, high, 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 low, and high, high, high. So now we've confirmed that we've designed in Quartus, we've simulated it, we've done it on our breadboard, and everything works perfectly.
And then we're going to do one more thing. We are going to just draw a real quick switch and LED diagram so that I can show you what Landa was talking about with the true position.
Let me turn off our
Share my screen. Share your screen.
All right, so is everyone good on the breadboard while he picks that up? I think the hardware side is definitely the most difficult, and you'll really feel that in that too, probably. But for this one, we good, right? Well, basically lab 0 review with more gates.
Yeah. Okay, so all right, Word really wants to just be front and center, so that's okay. Okay. So there will be a little like JPEG image on or a PDF as well, I think. Oh, wow. Okay. On somewhere in the website, I think it's in the lab page. Okay. Sorry about that. Okay. Okay. I don't know. Okay.
Alright,
Hopefully that'll work. Okay. But the basic idea is that you have a switch circuit.
let's close it all.
I have to close everything. Okay. Okay, so you'll find it on the website, but it'll basically just kind of be a box with a bunch of little boxes. And I made mine like really professional and neat, but I think on the exam and then practicals, you're just gonna have to draw it on paper. So basically, if it will ever let me show you, you will have boxes, switches, and then there will be like 8 switches. I think one for every of the physical switch you have, but I'm just drawing 3. And then LEDs, again, there will be more.
And then this is the switch and LED key. I don't know if he explicitly said.
Oh, I think I said just switch an LED legend or
Oh, yeah,
something.
legend.
Yeah,
So it's basically
diagrams.
Like your pi, you know. when
Oh,
you
it's
set
this.
Switch one, like what input that corresponds to.
Yeah.
And same for that.
Okay. So for switches, we know that the on position or the active like high position is going to be at the bottom. So for A active high, we're just going to draw it like this, right? And then for B active low, we're going to draw it up here because that is the true position for that switch. And then for C active high, same situation as A. And so it's really not that complicated, but all of these things help demo to your pi. So how Landon was going through each of the voltage table options and showing you physically is basically the same thing you're going to do at the end of lab 1. You're going to show maybe 3 or 4 possibilities for both your lab quiz and then for your pre-lab. So that's kind of how the demo works, is what we just did, except it'll be a little shorter because we did all of the combinations. All right, and then for LED, you'll just say, so we had F, active low, and then I don't think we don't draw anything, do we? Yeah, so we just denote it. As you notice on both the switches and the LEDs, you have like 8 of each. So it's very important to know which is which one, because if you have a bunch of LEDs and you say that one of them is supposed to work and the other one's supposed to be for a different circuit, unless you can clearly define it like it is here, we won't know. So yeah, I think that's pretty much everything you need to know for lab 1. Does anybody have any questions?
Aiden, right?
Yeah.
Alright.
What can some like the annotations?
Oh, annotation, that's an excellent point.
Oh yeah, good point. Okay, let me. Okay. How do I want to do this?
In fact, one no, or,
I can email it to you. Yeah, I just want to get it to your iPad.
oh, what are you doing?
I think so. See if that works.
Okay, while he does this, I'll kind of explain like the general idea of how you want to do annotations. So for this lab, you basically have a simple circuit, inputs and outputs. And then for your annotations, the most important thing is showing that your voltage table matches your simulation. Like for this one, like for us, maybe like the first, it was like the first 2 were high. So on your you might want to make those red. And then on your simulation, show the high parts, and then the low parts, maybe make those blue, and then circle in blue. So it just kind of makes intuitive sense as it follows. Now going forward, once you get into lab 3, and you get to sequential logic, which we'll cover on either Thursday or next Tuesday. It's basically like all of your circuit components are dependent on a rising clock edge. So a lot of things will change on this clock edge and it'll propagate through your design, kind of like pipelining kind of deal if you're familiar. So that's when the annotations get really important because maybe a 0 and a 1 will represent an instruction in a later lab. So this lab 1 and lab 2 is really just preparing you to make sure you understand your simulation and that you're able to explain it to your pi in the demo. So how's it going?
Almost there.
Okay, he's still working. Any other general questions? Does that make sense, Aiden?
I'm there.
Oh, yeah. Oh, what are
Josh, talked about this. It's about the.
is this like a general question?
So I get to you.
Yeah.
For grouping inputs on the waveform,
Yeah.
how do you get it so it counts like all the way up? Like.
Oh, okay. Yeah, we can just do that again. Okay. So when you open up your simulation, I'm just going to go ahead and change the end times right now. Okay, so you make them a group. Now you can either do that by like clicking this in control, clicking everything, or I just click the first one and then press shift and click the last one. Okay. And then if you right click and press grouping, you can make it a group. And you can call it inputs. And then you go to the C, which is the counter. And this is what saves you a lot of time. So I'm going to ask it to count every 25 nanoseconds so that it fills in this chart. And now it's filled in. Does that answer your question?
Yeah, for outputs, like you have two outputs,
Yeah.
like counting in binary, it's just like 0, 0, 0, 1, 1, 0, 1, 1, and then back to 0, 0. Is there a way to like match, like if I have 4 inputs and 2 outputs, like, so then you can see like.
Yeah. So if you have more than that, you can just drag these around. Does that make sense? So if you have more,
Yeah.
if you have to group
You can go
outputs,
ahead.
yeah, you can.
No, this is not.
Oh, yeah.
Yeah, so the answer is yes. You can group outputs the exact same way that I grouped the inputs. So if I ungroup these, I could even probably group these. Yeah. So you can just group anything you want, and then it will show, as you can see, it'll show you the numbers as you expected. Okay. Let me just do this. Okay. Now I'm going to run the simulation again. Okay. All right. So one thing you could do is label the output, like the low outputs, one color. So highlight them, maybe like a light blue, and make all of these a light blue. Or I guess you could make the boxes the same, that color, because it's
So that's not.
easy to see. And then make this a different color. Okay, so I'm just doing that as an example of something you could do. And then if I go back to here, okay, thank you for coming. Yeah, I'll probably post the video. Yeah. Okay. So I could go here and I could highlight this in blue, these in blue. and then these more in the yellow. And that way, it just shows to your pi that you know what the correct output is supposed to be and that you got it. It also helps prove it to yourself. So yeah, I think that's pretty much
Close
it.
this off real quick.
Yes, go ahead, sir.
All right. So for those of you who want more like help on a specific topic, these are all links to videos. So this is basically everything we covered today. Mixed logic, truth table, switch LED on breadboard, Quartus design and simulation. If you missed something specifically here, I'll actually full screen this. Since you guys are all have your phones out. Yeah, if you missed something specifically and want to go back, this is like a more concentrated and shorter version. They're all about 15 minutes. But yeah, that's gonna be the end of the help session. Joseph and I can stick around for a little bit to answer any questions, but yeah. So I think not in the recording on this too.
Step